Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to just give an example here of how integration by parts works. So what we're going to try to work out here is the integral of 4x times secant of 2x squared dx. Always important, I always want to comment, it's extremely important to know what method to choose. Integration by parts is a really good method when you're looking at the product of two functions that are of different types. So we're looking at 4x, which is an algebraic function, and secant squared, which is a trigonometric function. So that's your clue that integration by parts is going to be a good way to handle this. All right, so when using integration by parts, you want to choose your u, whatever's left is your dv. Then you calculate du and v. So the first thing you do is you choose your u. I always use this acronym to choose them, LI8, which again stands for logarithmic, inverse trig, algebraic, trigonometric, and exponential. I'm just going to go through those one at a time. So I look over here for a logarithmic function. I don't see one. Next, inverse trig function. I look over here. This is not an inverse trig function. This is a trig function. If it was an inverse function, that would be a -1. Next one here, algebraic. I look over here and say, yep, there's an algebraic function right there. Now, let's talk about the 4. Whether we take this 4 and group it with the u, or we just put it out in front of the integral, that's anyone's choice. I'm going to go ahead and just say u equals 4x. Once you choose your u, whatever's left is your dv. So in this problem, my dv is equal to secant squared of 2x dx. Next, we're going to calculate du. If u is equal to 4x, then du dx would equal 4, and therefore du is equal to 4 dx. Integration of the next term. Well, the derivative of tangent is secant squared. So the antiderivative of secant squared dx is tangent. Now, this is going to be tangent, that's a 2x, and I believe we're going to need a 2 down here because of the chain rule. When I check these, I usually run them forward to make sure I got the constants right. So the derivative of this function would be secant squared of 2x times 2. So the 1/2 is needed so that by the time I do the times 2, there's a 1 sitting here. So our integral, and I'm going to put OI, which in my notation stands for original integral equals. I'm talking about this. UV minus integral V du. So this is going to equal 4x times tangent of 2x over 2. That's this product minus the integral of this product. So that's going to be minus the integral of tangent of 2x over 2 times 4 dx. That's a times, not an x. I'll do that. I'm just going to go look this line over, make sure it's right. So our integral is going to equal this product, uv, minus integral of v du. So that's going to be tangent of 2x over 2 times 4 dx. Now, you notice we got another integral to work out, and that's okay. That's quite common. I think what I'll do here is write another line to simplify this thing down a little bit. So 4x over 2, let's write that. 2x times tangent of 2x minus 4 over 2 is 2, so let's bring that out in front. And we got integral tangent of 2x. And at this point, right here, really an integral has been done. So I'm going to put a plus c1 here and here for the fact that we have integrated part of this function. Now, in order to finish the problem, we need the integral of tangent of 2x. So what I'm going to do now is work on this. Oops, and to tell you the truth, I forgot my dx. 4 over 2 is 2, tangent of 2x, but there's that dx there. Can't forget that, very important. I'm just going to go ahead and work on that as a separate problem. Integral tangent of 2x dx. Now, tangent, integrating the tangent function, let's see, let's write that. Sine of 2x over cosine 2x dx. And now I'm going to do a substitution here. I'm going to let u equal cosine of 2x. Du would then be minus sine of 2x dx. Now, as I look here, I don't have a minus sign, but that's easy to supply. Minus, minus. This product is now equal to du. So I'm going to rewrite this integral. We're going to have minus integral du over u, which is minus ln of u.
Wouldn't your du be minus 2 sine of 2x?
Oh, whoops, and one of my helpers helped me catch something else. I go back. Let's see. If u is cosine of 2x, du is minus sine of 2x times 2. Yes, there should be a 2 right there. Thank you very much. And then we're going to want to do that. That. This has a minus 1/2 in front of it. Okay, so this is going to be minus 1/2 times natural log of cosine of 2x. Whoops, and I should not put equals. Those are different integrals. All right, so now we have to kind of put this whole thing back together again. This part, integral tangent of 2x dx is equal to minus 1/2 natural log cosine of 2x. So the original integral, OI, is equal to, I look back through my work, 2x tangent of 2x. There's this part. I'm going to go ahead and underline what I just did. Right there. That's now right there. Minus 2 times, I'm going to circle this in red, integral tangent of 2x dx, which we just worked out to this. So when we do the minus, that's going to become, when we do the minus times a minus, that's now going to become a plus 1/2 natural log cosine of 2x. Now, really there should have been a constant on here. Let me kind of backtrack the constants. We called this one a C1 from the first integral that was done. Another constant has been, another integral has been done, so technically this has a second constant, C2. By the time I put these together, they add to a third constant, which is C3, and that's done right there. So integration by parts is all about really just following the formula. I usually work these by pattern. Pick a u, whatever's left is dv, calculate du and v, and then your integral is equal to this product minus the integral of this product. They always end up having to work out 2 integrals, or sometimes more. But you see how effective they are at anti-differentiating a function that's got 2 different types of functions involved. So, hope this example helps. I think I'll gear up for another one, and have a great day.